Hi everyone, this is Mr. Rob, and you are watching this free fall subject for physics or energy and motion. Now today we're going to talk about free fall. Free fall is basically falling freely or without anything to stop you. In real life we have this thing called air resistance. So if you see for example the in the center, you see this one here, you're seeing this kind of astronaut jumping out of a capsule, and it's jumping and it's going down freely, but really the air is stopping him a little bit. Here no air resistance, he's just falling on the floor. On this one here we have air resistance. When you get to a certain velocity, the air will stop you. We're going to talk about that also. And on this image you're going to find that if you throw something that is very big and heavy, it's going to fall at the same rate as something that is small as a mouse, and they're going to fall at the same time. So let's begin. Free fall. The constant acceleration of an object moving only under the force of gravity, that is what we call free fall. So basically gravity is pulling this object or yourself down into the center of the earth. And gravity is it's an acceleration. If you can see it, this point here, the acceleration caused by gravity is 9.81 meters per second, and as you know, meters per second is the unit for acceleration. And 9.81 is the acceleration that you have when you're falling. Basically you will get a higher velocity, so each second you're going to have a change in velocity of 9.81, and we're going to talk about that later on. If there was no air, like if we were like in a vacuum, like on the moon, all objects will fall at the same speed. Basically only air resists for us to move. You can understand this a little bit better if you try to move in water. The water is going to stop you at a lower velocity, but if you move in air, well, you need a higher velocity to stop you, but still it's going to stop you. The free fall doesn't depend on mass or the time that it takes, or it doesn't depend on the mass, meaning if you remember, this elephant has a higher mass, more kilograms, and it will take the same time to fall, or he's going to get the same acceleration as the mouse, and that's basically it. Now after 1 second, the velocity that you will have is 9.81 meters per second. That means that on the first second, if you throw something from stop, like from rest, the first velocity in the first second is going to be 9.81 meters per second. After the second second, it will be twice g, or 2g, 19.62 meters per second. And at the third second, it will be 29.43 meters per second. That will be the velocity, getting higher and higher each second. So the change in velocity, that means acceleration, is going to be 9.81, and it's constant. Now Galileo Galilei, this guy in the 1600s, he studied how things fell, and he didn't at the time have a very good clock. If you try to think on it, they didn't have like electronic devices. Now we have them, like on our cell phones, iPhones, iPads, on our computers, etc. Back then they didn't have it, so he did something different. He rolled balls down an inclined plane, and this way he will see it better, like he will see the comparison between them. He found that the speed increased as it rolls down the ramp. Basically they were falling, but in a horizontal downward direction. This is like the ramp, this little triangle here, this one here. And acceleration, he said that it was the change in velocity in time. For example, you have a t0, you have a velocity equal to 0. In 1 second, do you see how it moves? So velocity there will be 9.81, then 3 times g, 2 times g, sorry, 2 times 9.81, and 3 times 9.81. That will be the velocity. But do you see the difference between this? So higher, more time, higher distance, higher distance. The same thing happened when things fall just straight, like for example that 1 second, third, fourth, fifth second, and do you see it covers more distance each time. One thing about Galileo is, sorry guys, he didn't drop things from the Pisa Tower. That's a lie. Someone thought of that, but that's not true. Now, falling. When falling, air resistance will increase as it falls faster, and that means that when something is falling, the air is going to try to stop you, right? So an upward force is this resistance of the air. Eventually, gravity will balance with air resistance, and that will mean that you will not change your velocity anymore. So you will have a velocity that will be constant, and that velocity is called terminal velocity. So it reaches terminal velocity, highest speed reached by falling object. That is the highest speed that will be reached by a falling object. There's two guys. So they will be falling, and there will be just a certain velocity that they will get, no more. The force of gravity, we said, is constant. It goes down always at the same rate. But air resistance increases as you speed up. If you go faster, then faster, faster. Do you see the other arrow going up? And there's a time that when they will be equal, will be the same. At that point, when they have equal forces, so the force of gravity is the same as the force of resistance, there will be no acceleration, meaning that you will have a constant velocity, or it is called also terminal velocity. Here you have another a guy dropping here this baseball, and he's dropping it, and do you see it's falling faster than a sheet of paper, right? And that you can do the experiment. We'll do it there at in our class. Now in this case, when you get this piece of paper and you just make a little ball out of it, they will fall at the same rate, and that tells us that really mass doesn't have anything to do with it. Of course, the baseball is going to be heavier than the paper just made into a ball. Now this is an air-filled tube. It has air, so a feather will, because of air resistance, it will fall with a lesser velocity than a stone. But if you take all the air out, they will fall at the same rate. And this was done. This experiment was carried away on the moon, and they threw a hammer and a feather, and basically they fell at the same time. Now let's do this example. Falling from a tower. Suppose that a ball is dropped at when we said it's dropped, we mean zero velocity, from a tower that is 70 meters high. So it's very high. 70 meters is a lot, right? How far will the ball have fallen after a time of 1 second, 2 seconds, and 3 seconds? Basically what they're asking is the distance, right? So the solution that we have for this, and if you remember the equations that we had, we can get the first equation. Distance equals initial velocity times time plus 1/2 of acceleration. In this case, it will be g. The acceleration will be the gravity times to the square. So, or time to the square. Now, the initial velocity is 0, so we get a 0 there, plus 1/2 of acceleration time to the square. So basically, we only have this this part, so it's 1/2 of 9.8. You will find this most likely like 9.81. This is that 9.81 will be an approximation, but you can also put 9.8. It will give you a less accurate answer, but this is the same. So we have 1/2 or 0.5 multiplied by 9.8 times 1 second to the square. That will be 4.9 meters. This will be the distance traveled by any object dropped from an initial velocity of 0, like from rest. So the ball has fallen a distance of 4.9 during the time interval from 0 to 1. We will do the same for 2. So we will get the same 2. You see distance 2 or y2. Why? Because it's in the y-axis. That's why. A lot of y's. So 1/2 of acceleration times 2 to the square is 1/2 of 9.8. 2 seconds to the square. So this will be 4. And do you see the huge difference between 1 second and 2 seconds? This means that in 2 seconds, if you throw something from a height of 19.6 meters, it will take 2 seconds for the object to hit the ground. And almost 20 meters is a lot. What will happen at 3 seconds? Well, you will need a building of 4.1. Same thing, 1/2 of 9.8, 3 to the square, which will be 9, and then it's 81 divided by 2, 44.1. So this is a huge difference, again, a little more than double. And basically, that's when we mean dropped, we mean that the velocity equals to 0. That's this problem. Let's go to